This video is sponsored by PCB. Today I'm going to be fixing an issue that's plagued my solar system since day one. Once the batteries are below 20% SOC, they will tell the inverter that they need charging via their communication protocol, which will then turn on the generator by closing these contacts. This on its own would be weird since there is no option in the inverter's settings to choose a back to grid SOC, only a voltage, but the issue is that as soon as the batteries reach 21%, the generator is turned off. And this is bad for the batteries. They don't like being charged and discharged repeatedly. It's also annoying to hear a generator stopping and starting all the time, and probably not good for it either. This is how the generator and the inverter are wired together. My plan is to put a device in between the generator and the inverter that will decide in a more clever way when to turn it on and off. I was originally just going to throw an ESP32 and an RS-232 converter on a perf board, but PCB reached out to sponsor this video. While my PCB was being made, I used my breadboard prototype to try out the communication between the inverter and the Arduino. The communication protocol itself isn't that complicated, but it does have a CRC, and since I know nothing about CRCs or how to implement them, I had to steal the code from another project. And after finally getting the communication to work, I moved on to designing the PCB. After about 2 weeks, I came up with the following schematic. You're gonna have to ignore the obvious mistakes. I then ordered the PCBs and their assembly through PCBWay, and when they arrived they were basically perfectly packaged. Each PCB had its own anti-static bag and they were all assembled perfectly. So yeah, thank you to PCBWay for sponsoring this video. If you've never made a PCB and would like to give it a try, it's honestly quite easier than you think. There should be a link in the description. To test the ESP32, I uploaded a blink sketch, but I used the relay instead of an LED. I then started writing the code for it. This was probably the hardest part, since I wanted it to connect to Wi-Fi and host its own server where we would be able to see statistics of the inverter without having to use that spyware WatchPower application. This is the main part of the code. It decides if the generator is turned on or off. If the battery's SOC is below 20% or their voltage below 47.5, it's turned on. And it will be turned off once the batteries reach 25% or the power being generated by the solar panels is close to the power being used by the house. I would just like to show you the beautiful code that I wrote to sort the response of the inverter into separate variables. After I finished the code, which is by the way on GitHub, I took the board and a power bank to test with the inverter. I then, as any sane person would, opened up my 3DS to check if everything was working. What I actually did was make an app using MIT App Inventor, which is basically Scratch Mobile, and then I was able to check it on my phone. I also implemented some buttons so I'd be able to control the generator. I definitely did not want to implement that into the HTML. While doing the permanent installation, I noticed that the inverter does not have the 12 volt output port that it said it did on the manual. I then realized that it's optional, and mine doesn't have it. So I had to improvise by using a phone charger and powering it off USB-C. I could have avoided doing all of this if I'd just used a Raspberry Pi and this brilliant project, but I wanted to prove that an ESP32 is enough and also create my own project that I could be proud of and learn stuff along the way, like PCB design. Before I said that the CRC generation was the hardest part of the code, but I now think it's the Wi-Fi. For some reason, the ESP32 Wi-Fi library for Arduino has a problem maintaining a connection for over 2 hours, but I think I've finally been able to solve that by modifying some part of the code that reconnects if it loses connection. I somehow managed to do the funny thing that all PCB designers do and put the UART the wrong way around. Here's something that actually isn't a skill issue. I didn't get the pin out wrong for the DB9 connector. The reason our cable is stripped and soldered directly to the board is because I had to do some measurements to reverse engineer the pin out for it. Since I'm also installing one of these boards in our neighbor's house who has the same inverter, theirs will not be soldered directly to the board and I can use the connector. The reverse engineering of the connector also led to the funniest purchase I've ever made.